Alright, in this video, we're going to continue our discussion about gases by looking at a very important property of gases, and that's the pressure of a gas. Okay, now, a pressure is a force that is exerted by a gas due to its collisions with the walls of a container. So, for example, if you consider a big red balloon here, okay, that red balloon holds its shape because there are particles inside of it of a gas, usually air, but it might be helium or something else. Okay, and those particles are zipping around really quick, bouncing off each other, but also bouncing off the walls of the container. Okay, that force that's being exerted is the pressure of the gas. And anything that we do to affect those collisions is going to have a profound impact on pressure. So overall, what we can say here is that pressure is proportional to the frequency of collisions between the gas and the walls of the container. Okay. Now, as you can imagine, the pressure of a gas can be affected by a number of different parameters. So specifically, if we think about things like temperature and volume and the number of moles of the gas present, these are all things that will affect how frequently one of the particles of a gas will collide with the walls of its container. And we're going to find that anything that affects that property is going to affect the pressure overall. Now, I do want to point out that, when you put a gas into a balloon, the balloon expands, right? But have you ever wondered why it doesn't keep on expanding? I mean, surely, the balloon itself has some integrity to it, so it's not going to just break. But we know that balloons can break, so why is it that the balloon doesn't just keep on expanding? Well, it turns out it's because there are particles of a gas both inside and outside of the balloon. Okay, so balancing out those collisions on the inside are the collisions that are taking place from the outside. That pressure is what we call atmospheric pressure. And I'm going to symbolize that as a capital P with a subscripted ATM. Okay, now, atmospheric pressure is going to change depending upon where you are on the planet, with possibly the biggest impact being the altitude that you're standing at. Now, atmospheric pressure is roughly 15 psi. And I'm sure we've all heard about psi from putting air into our bike tires or into our car tires. But a psi stands for a pound per square inch. And where this originates from is the following. Okay, so imagine the Earth. Okay, so we have this big sphere. And we know that the Earth has an atmosphere. Okay, so we have this blanket of gases that are floating over top of us. And as we get further and further away from the surface of the Earth, the density of the gases decreases. In other words, there's a lot less of it as you go higher. People will say things like the air is thinner, but that's what they're talking about. Okay, now, we tend to think of gases as being things that are completely immune to gravity because they just sort of float around. But that's not entirely true. Gravity does have an impact on gases. In fact, that's one of the reasons why the gases stay on our planet and don't just dissipate out into space. Okay, so if you were to take a postage stamp, okay, and lay it on the ground, maybe on a sidewalk in an open area. And then imagine extending the borders of that stamp out into the furthest reaches of our atmosphere. Okay? Some of those air particles are going to be within the borders or within the boundaries of the walls of that stamp. Now remember, the stamp is about the size of it's 1 inch by 1 inch. So the stamp is about a square inch. So what we have is a column of air that has a footprint of 1 square inch on the surface of the Earth. And if you were to measure the mass, or I should say the weight, of all the air particles that are in there, in that region, it's going to equal about 15 pounds. Okay, so 15 pounds being applied to every square inch of the surface of Earth. So 15 psi. Okay, now pounds per square inch are a useful way of measuring pressure. However, it's not something we like to use in chemistry, mostly because we're dealing with pounds and inches. We want something that's a little bit more metric. So we have other units that we can use, many of which do take part in the metric system. So we have things like pascals, which oftentimes you'll hear about kilopascals. We have bar. We have torr. And if you look on the news, you'll see that the barometric pressure is usually going to be reported in inches of mercury, which sounds kind of weird. But we'll talk more about that in a little bit here. Okay, and then in chemistry, we like to use a unit called the atmosphere. Okay, now, the way that we use the atmosphere is by saying that atmospheric pressure at sea level equals 1 atmosphere. Okay, so why does it matter if we're at sea level? Well, again, like I said earlier on, depending upon what your altitude is, that's going to determine how many particles of air are over your head, and therefore the amount of atmospheric pressure you're going to experience. Now, in addition to the atmosphere, we oftentimes utilize a unit called the millimeter of mercury. And it turns out that 1 atmosphere is equal to 760 millimeters of mercury. So you're probably wondering, how is it that we're going around trying to calculate or trying to express a force in terms of the distance of a substance? And that doesn't seem to make sense until you understand the experiment that produces this value. All right, so here's how that whole experiment went down. So imagine having a glass tube, and the glass tube is open on one end, and it is closed on the other end. And then you have kind of like a dish, like a shallow dish, that you fill with mercury. Okay, so we'll use green to convey mercury. Okay, so we put mercury into this dish. Okay, and then we fill up the tube with mercury. Okay, now imagine that you take that tube, put your thumb over the top of it, and flip it upside down. And what you wind up with is something that looks like this. You have your dish, and then you have your tube inverted inside of it. Okay, and of course we still have the mercury that's in the dish. And we have mercury that's still in the tube, except we would expect that due to gravity, that the mercury would drop down in terms of where it is on the tube. So we have that kind of like a little vacuum just above it. Now, the reason why all the mercury doesn't come out, well, it's a combination of two things. That vacuum and also the pressure of the atmosphere pushing down. Okay. Now, if you were to set up this apparatus at sea level, what you would find is the following: that if you were to measure the distance from the top of the mercury in that column to the top of the mercury that's in the dish, that distance is 760 millimeters. Okay, which is why we can say that at sea level, atmospheric pressure is 760 millimeters of mercury. All right, we just need to make sure that when we're doing our problems that we're careful to make sure that we convert units to the proper pressure unit. And you're going to find there's going to be some circumstances where you'll use the millimeter of mercury and some where you're going to use the atmosphere.